Our last talk for the morning is Polishchuk, who is going to tell us about Schwartz spaces located in this market, random bundles over a long period. Okay, thank you very much. It's a great honor. I met Maxim at the late 80s. I was a very fun seminar. I was assigned as a teacher for a group of students. And I remember that it was not always easy to understand what Maxim was saying, but we quickly learned that you have to try to catch every word. And I tried to do that ever since. I tried to find a photograph of Maxim building a house later with my son at or my residence. I couldn't find it. It was too long ago. Anyway, it was fun spending also summers there. Anyway, so I'm going to talk about our joint work with Sasha Braverman and Kazhdan, and it's about Schwartz spaces. So motivation comes from, so I'll remind you a little bit where this picture comes from. So in classical Langlands for the function field, one considers modulus of bundles over curves of the finite field, but then one considers functions with finite support by the more bundles. And there is an action of Hecke operators and parameterized by points and the covates of the group. And so these multiply bundles near a point. And so this is a commuting algebra and the kind of common eigenfunctions. And so therefore, there is a relation to the Galois side. So some interesting story about eigenvalues and so forth. And it was proposed to there is an analog of this picture when the finite field is replaced by a local field. So it could be an Archimedean field, you can take even complex numbers or real numbers, or it could be non-Archimedean local field like power series of a finite field or Gatic numbers. And so in this case, there is still a reasonable interesting notion of kind of functions on the some kind of Schwartz functions on the modulus stack of bundles, but now one has to kind of take into account the topology. And so the reason we're interested in this space, so I'll define the space. The reason we're interested in the space is because the eigenfunctions, the common eigenfunctions of the Hecke operators are going to live there, and so this kind of provides some interesting information about how these eigenfunctions can look like. So there is actually one work of Maxim where he considers these Hecke operators in the example of P1 with 4 points, group SL2. So there is kind of I'm not going to discuss general conjectures. So there's some supposed to be some M2 space where some compact operators act, but this is all kind of described, this conjectural setup described in a series of papers of Ettinghoff, Frenkel, and Kazhdan. So in this talk, I will only discuss with Schwartz spaces, and in a particular example of rank 2 and bundles with fixed determinant. Okay, so let me first recall a little bit about the Schwartz spaces. So I will consider the case of a non-Archimedean field. So there is an analog of all kind of in Archimedean case, kind of based on the works of Eisenbach and Gurevich, but it's much easier to discuss what happens in non-Archimedean case. So in this case, so if you just have a variety over non-Archimedean local field, so we just consider locally constant functions with compact supports on the corresponding periodic variety, and in this case on the set of F points. So if you kind of don't work much with this, here is a quick example. So if you're considering just a fine line, so just the field itself, so if you consider delta functions of integers, so this is an open, this is like a ball for radius 1, so the delta function is locally constant, but for example, if you multiply it with absolute value function, this is not going to be locally constant near 0. So This is an example of continuous but not locally constant functions. It's not in the Schwartz space. Right. So more generally, we're going to consider kind of twisted things. So we're going to consider, for example, a line bundle, and then so the line bundle is given by some transition functions on respect to open covering. And so if you have any character of your field, for example, just take power of the absolute value. So take complex power of absolute value, apply the transition functions, and out of the algebraic vector bundle, you get this C-star torsor, and you can consider sections of this. And in this way, for example, if you apply this to canonical line bundle, you get things that you can integrate. You get densities, and so it's it's a kind of classical picture going back to André, but kind of this type of integral is related to the number of points over reduction. Right, and more generally, we'll need the push forwards with respect to smooth morphisms. So whenever you have smooth morphisms between varieties defined over non-archimedean local field, you have the corresponding push forward of Schwartz sections. So if you start with something locally constant and with complex support upstairs, and you just integrate over fibers, you get Schwartz function on the base. So if you start with a morphism which is not necessarily smooth, then things get more interesting. You can still define push forward. Well, if you start with a distribution with complex support, you can still define push forward as a distribution, but then it may be given by a locally constant function or by some kind of other function, and not necessarily. So there is a very important theorem by Eisenbach, which gives a characterization of morphisms for which push forward is given by continuous density. So this is so the assumption is that morphism should be flat and all fibers should have rational singularities. So I'm not going to define what it means now, but because this will play a role, I will remind what are rational singularities at some point. Right. So now, when we're interested in considering the spaces for the stack of bundles, so this is not a variety; this is a stack. So, so let's consider what one should do for a stack. So this actually was done in the work of Dennis Gatesbury and Kazhdan. So they considered kind of, well, so for example, we can just start with a quotient stack, which is the algebraic variety with an action of a group, and then you take kind of this stacky quotient. Now I assume that the group is GLM, so it's not to have any kind of non-trivial torsors over this group over base field. And then so the basic idea is that now you can consider, you can start with Schwartz functions or Schwartz kind of twisted functions by some line bundle on the corresponding variety, but then there will be on the space the group will act, and you're supposed to consider co-invariance. So co-invariance is like the maximum quotient on which the group acts trivially. So this is a purely algebraic construction, but that's that's kind of some. So the reason is that the Schwartz functions they kind of behave well with respect to push forwards, not pullbacks. So I mean pullbacks too, but the compact support is not preserved on pullbacks. So you don't have actually to do it for a group. You can start with any presentation, and then it will be some coordinate rather than linear. So this was. By the way, this also works in an Archimedean case, and this was considered by Sekularitis. So yeah, this is actually there is an Archimedean story as well. So if your stack is not necessarily of finite type, like the stack of bundles, so you can apply this construction to open substacks of finite type, which can be presented as such quotients, and then pass to elite. So right, so yeah, in the case of bundles of vector bundles with Higgs determinant, we can just kind of rigidify the stack by considering realization of a multivisor, and so this will kind of provide such a structure, such a presentation of the quotient for open substacks, and yes, but you have to consider this type of limit. So, but whenever you consider some particular Schwartz element of a Schwartz space, it will be supported on some open substack of this type. So you can always think of it in these terms as having some family of bundles parameterized by variety with an action of a group, and you're considering the G orbits correspond to isomorphism classes of the corresponding bundle. Right. So in this analytic Langlands picture, it turns out that the relevant twist is half-densities. So you have to take canonical bundle and take 1/2 power of half, and that's exactly what Hecke operators act. So this corresponds to some calculation with line bundles, which I'm not going to go over because, as I said, in this talk, Hecke operators will not appear. I will just be interested in Schwartz space, but this 1/2 will appear in the following form. I will be kind of studying properties of this elements of the Schwartz space, and kind of turns out that this 1/2 is a kind of critical value. So you can things behave nicely for this complex power with real part at least 1/2. Yes, that's right. So they do have an even product, and but well, actually, no. It's not clear because I mean, if this were a variety, yes, but that's actually part of motivation. So we want to replace the type of bundles by sufficiently nice open subset of stable bundles, and then to prove that the Schwartz densities restrict to some L2 functions there, so that there will be a yeah. So Paul is absolutely right. So actually, the goal of the story is to equip it with the pairing, so that you can complete, and then the Hecke operators will act on this completion as complex operator. Right. So here is kind of the general question one can ask. So suppose you're considering a stack which is a quotient of X by group G. So, and suppose you have some nice invariant subset on which the group acts free, so that there is actually geometric quotient. And then kind of it's natural to think that elements of the Schwartz space of the stack will give rise to some functions on the orbits, of the space of orbits phi of G. But it's actually not clear that this will always be the case, because you have to integrate over orbits, and the problem is that so you start with a Schwartz function defined on X, so it has a compact support on X, but then you restrict to U, and at this moment the compact is no longer compact. So so then there might be a problem with integration. Here is a very simple examples. You take A2 with the standard action of the multiplicative group. So then on the subset where one of the coordinates is not zero, there is a quotient. You just take ratio of coordinates y over x. And so you take the simplest possible Schwartz density. So you just take characteristic function of the whole radius 1, multiply the standard realization of the bundle. So yeah, the bundle here is the canonical bundle to the power of some complex power kappa. And then the corresponding integrals, you will see that there will be some power here, and so the convergence will depend on whether this kappa is big enough. So if kappa bigger than 0, this will converge. Otherwise, there might be some divergence issue. So one has to be careful. So now in the case of bundles of rank 2 with Higgs determinant, so we consider, so so we do have such a open subset. Well, almost. So you consider stable bundles. So they still have some finite automorphism. So strictly speaking, it's not a variety, but still a DM stack. But this is a minor issue. We can pretend that they are varieties. But in addition to considering stable bundles, we will also consider a smaller open of very stable bundles. So I recall that a bundle is very stable if it doesn't have any important Higgs field, non-zero nilpotent Higgs fields. So now the first main theorem of this talk is that if real part of kappa is at least 1/2, then any element of the Schwartz densities, we consider this kappa densities. So take a canonical bundle or rather corresponding C torso to the power of kappa. So any sections like of this Schwartz space, so they have a well-defined restriction to not to the stable open set, but to the very stable open set. So if we consider orbits corresponding to very stable bundles, then the claim is that all the integrals will absolutely converge and will define locally constant function on the corresponding open set. And yeah, the second part of the theorem is maybe less important, but it's kind of just nice to know that this Schwartz space actually doesn't. So the stack of bundles is of infinite type, but there is always a sufficiently large open substack of finite type which has the same Schwartz space. Right. So again, the issue with integration was that the orbits in the open set that we're interested in are not necessarily closed in the bigger variety. So in our case, this actually very well happens. So when you consider orbit corresponding to a stable bundle or even very stable bundle, if you're starting with the density, start with a Schwartz density, which involves not necessarily stable bundles, then the orbit will not be closed there. So, and this corresponds to the fact that there are families of bundles which are kind of isotrivial away from a point and correspond to any given very stable bundle. But in the limit, you can get something which is not stable, just direct sum of two line bundles, and this is just obtained by you just represent your bundle as extension of two line bundles, and then you can pass to the limit where it degenerates into direct sum of two line bundles. So this convergence issue you do have to check something. So there are kind of bundles that are in the closure of very stable ones. Okay, but it turns out that there is actually more control in the case when you start with not just a stable bundle, but a very stable bundle. You actually control better what kind of limits you can get. So it's actually a crucial part. So the claim is that if you consider a limit, if you consider kind of specialization of a very stable bundle, so here B is very stable and B0 is a specialization, then not only it's always a direct sum of two line bundles, but also in this direct sum of line bundles, there is no x1 from one line bundle to another. This means that these two line bundles cannot be of two, the degrees cannot be too close to each other. The degrees have to be kind of sufficiently apart depending on the genus. Right, and so here is a sketchable proof of this. This is a kind of easier argument. So suppose you have this limit. So first of all, we know that it's not stable. So it has some destabilizing subbundle L2. So we consider this destabilizing exact sequence. So degree of L2 is bigger than the slope of or equal. And then the only part where we use the denote as a specialization of B is to claim that actually the home from B to the naught is not zero. This is because if this home were zero, then it would also be preserved under small deformation. So instead of V naught, we would put B there, but home from B to B is obviously not zero. So therefore, this would be contradictory. So now by stability, so because there is no home from B to L1, so we actually know that home from B to L2 should be non-zero, and so at this point, I assume that this non-zero form from V to L2 is surjective. This is the only reason why this is not a full proof, but only sketchable proof. So if it's not surjective, the argument has to be slightly modified, but it still works. So supposing that the map from V to L2 is surjective, you get a sequence for V with the same line bundles because the determinant is fixed, but in the opposite direction. And then now you can see that this implies that there is no form from L2 to L1 twisted by canonical bundle. Otherwise, you could construct the nilpotent Higgs field on V as follows. So you start with V, project to L2, then go from L2 to L1 tensor omega by a non-zero map, and then embed back into V tensor omega, and this would be nilpotent Higgs field. Because we assume that V is very stable, there is no such, so therefore form from L2 to L1 twisted by omega C is 0, and by star duality, this means that there is no x1 from L1 to L2, so therefore the node splits. Okay, so this is used in the following way. So we need to so the general setup where we try to define, we start with some x with the action of a group. We have an open subset U, and we start with some Schwartz distribution on x, which is Schwartz function on x, which we want to integrate over orbits in U. So we want to compare, or maybe it's even smaller than U. So something, so U could be kind of anyway. So U could be some invariant over. So basically, we want to compare the Schwartz spaces, which are defined as this co-invariants, for x and for U, for the smaller over. And the claim is that for this, you have to check something at every point of the complement. So, and what you do is you look at any element of a complement, and you assume that the stabilizer has a multiplicative subgroup, so it has some co-weight down the check. So that then you compare you compare two characters on this co-character of the stabilizer subgroup. So one character comes from this line bundle. We're interested in this line bundle L. So for every point x, we can consider how the stabilizer group G sub x acts on the fiber of this line bundle L at x, and this gives us one character. So this is the character appearing on the left. On the other hand, there is some standard character coming from quadjoint action of the stabilizer subgroup. And so basically, there are some, so this gives you restriction on which powers of kappa you can consider. So if kappa satisfies this inequality, then it turns out that every element of the Schwartz space on X actually comes from the corresponding Schwartz space on U. So this is, again, because there is this quotient by G, this means that we're considering spaces of co-invariants. And furthermore, if there is some more information about the stabilizer group, so it's just there's this multiplicative subgroup and then semi-direct product with the addition group, then not only this map is subjective, but in fact it's an isomorphism. Right, so here is a toy example of how this can happen. So suppose your variety x is just a line, and then you're throwing away 0, the line bundle is omega. So we consider delta function of the ball of radius 1, and we want to check. So this is something which is by definition doesn't live on U, it lives on the pole x. But we claim that in co-invariance, actually it comes from something which is supported on U and away from 0. And for this way, we just observe that when we apply when we rescale this delta function, we get a delta function of another ball, and times some factors. So when we subtract, we get a delta function which of an annulus, so kind of difference between two balls, and so therefore this is already something which lives away from 0. So in co-invariance, assuming that some factor is not 0, this q to the kappa minus 1 is not 0, you actually can realize the same element of the Schwartz space living on the smaller orbit. Okay, so that's kind of very roughly the idea of the proof. So, but in the proof, you have to do this for every orbit in the complement. So you have this X with the action of G, you have a smaller open set U, you have to consider every orbit in the complement, and you have to check some inequality of characters there. So there will be there is a standard techniques how to reduce to considering every orbit, and then so the corresponding Schwartz space on the orbit is just induced representation from the representation of the from a character of the stabilizer subgroup, and so using this we get this extension lemma. So then this allows us to kind of this gives us a general techniques of how to extend, if we already know that this integrals over orbits are well defined on some open set U, then it gives us a criterion that we can extend this to kind of Schwartz functions coming from X. And in the application to the stack bund of bundles of rank 2, we apply this to this standard filtration of the stack by bundles which are kind of less and less stable. So we can measure stability by kind of assigning kind of what degree of lines of bundles can have. So we can have larger and larger degree, which gives us a standard filtration one less than or equal than n. And so the idea is that we can kind of check exactly which kind of characters of the action of the stabilizer on the section on the fiber of the canonical bundle we get at points of the complement. But well, it's a little bit more tricky because one has to proceed in two steps. So when you consider the kind of difference between this substack where you allow subbundles of degree n and subbundles of degree n minus 1. So there is this intermediate substack where you allow subbundles of degree n, but only in the case when there is a corresponding splitting. So you have you allow subbundles of degree n, but only when V mod A has no x1 to A, so in particular this splits. And in this case, you get this multiplicative subgroup in the group of automorphisms, which satisfies the assumptions required in this extension lemma, and therefore this extension works. On the other hand, it turns out that kind of going from this intermediate substack to the bigger stack one less than or equal to n is okay, because the limits of very stable bundles do not appear there at all. So when you kind of increase your open subset in such a way that the orbits you're interested in, the closures do not intersect this complement, then actually the extension is needed. So this is how roughly this result is proved. Okay, so the next question is what happens when you try to analyze what happens with these elements of the Schwartz space, not necessarily at very stable bundles, but just at stable bundles. Okay, so here things get a little tricky, but there is a general conjecture which we don't know how to prove in general. Is so how we will always get some continuous densities. So this very stable locus, so it's an open subset kind of complement to some divisors. There we know that we have a smooth function, we have locally constant function. But when we look at what happens at stable but not very stable locus, the slopy divisor, then the hope is that they still extend to continuous sections. So we don't know how to prove that, but we have some weaker notion which is still enough, for example, to check that we have L2 property. That, for example, in the case of half-densities, this is enough to prove that the pairing is well defined. So this is what we call bounded distributions. So these are kind of functionals on densities such that there is this inequality in terms of the integral of density with some fixed constant kind of near on every component neighborhood B. So there should be some constant such that you the result of the action of this function is at most the integral times this constant. So for example, if you know that you have a distribution which is already smooth and some open, then this boundedness exactly means that it extends to a bounded function on every component. Right, so from now on, I assume that we consider determinant of odd degree. So L is this fixed line bundle is the determinant of our two bundles. And we also assume that the characteristic is zero, so we're considering paired case, not functional case. But hopefully this second restriction is not so, I mean, either of these restrictions should be very important, just more convenient. So we introduced certain algebro-geometric conjecture, which we prove will imply this property of Schwartz functions we want on stable bundles. So suppose we take any rank 2 bundle, take any stable rank 2 bundle of degree 2g minus 1, a curve of genus G. So then with this bundle, you can associate a certain scheme which lives over the Jacobian. So for every psi in the Jacobian, you can consider global sections of V tensor with this psi. So when you take a bundle of degree 2g minus 1, it always has at least one section. And generically, it has exactly one section. So this is actually this FB, so this is going to be a scheme over the Jacobian such that over psi, you just take projectization of global sections of V tensor with this psi. So it's actually maps birationally to Jacobian. So you expect it to have be reducible of dimension G, but actually our conjecture is not only that. So we conjecture that it's reducible of dimension G and has rational singularities. So after we actually posted this conjecture, the part that it's reducible of dimension G was proved by Olivier de Bar. But this is actually an easier part. So the part of rational singularities is still wide open, except in some low genus case, which I will point out. So let me remind you quickly the definition of rational singularities. So it's given in terms of resolution. So you take a resolution of singularities, so you assume your variety of normals, you take some resolution of singularities, and then you take derived push forwards of the structure shift. And it should be, it should be, so the high derived push forward should be 0. So the full derived push forward of structure shift on the resolution should be just the structure shift of x. And there is an equivalent characterization that the variety x should be Cohen-Macaulay, and in terms of resolution, just the usual push forward of dualizing shift on x twiddle should give dualizing shift on x. So,
so D has fixed determinant.
Actually, for this conjecture, it's not important. You just take any rank. You fix the D. No. To define this FD, you fix D. So you fix a vector bundle of rank 2 in degree 2g minus 1. And then with this, you associate a scheme which lives over the Jacobian. Just look. So this is scheme of FB. This is some kind of it's related to some kind of degeneracy locus. So you can consider the degeneracy locus inside Jacobian, where this V tensor C dimension of H naught of V tensor C jumps. So this roughly speaking, this FB is a blow up of this degeneracy locus. Right. So the reason this conjecture plays a role is because of this Eisenbach-Afni theorem, which says that when you integrate along a flat morphism where fibers have rational singularities, then push forwards of Schwartz densities will give you continuous functions. Okay, so here is our second main theorem. So we claim that Right. So when assuming that this algebro-geometric conjecture holds, we can prove that the densities we get from, so we can prove that Schwartz densities give bounded distributions on the stable locus. So, so when you consider this integral over orbits, so on the very stable bundles, you get locally constant function, and on the when you look at what happens in stable locus, at least we know that you get bounded functions. And actually, yeah, we can check the conjectural of genus, so for genus 2 and for genus 3, assuming n non-hybridity curve. And in the case of genus 2 and half equals exactly 1/2, we can prove that even stronger condition holds that we get continuous functions on the stable locus. Back to conjecture, yeah. Yeah, so the way I wrote it, so yeah, so the fact that it's irreducible in dimension G, this is not a conjecture, it's a theorem now, but yeah, it's a theorem of debug. So the fact that they are local complete intersection, if they are of correct dimension, this is easy. This is due to this determinant kind of the genus setup. So it's associated with some map of bundles from bundle of degree n plus 1 to bundle of degree n. And from this setup, it follows if it has correct dimension, then it's a local complete intersection, right? But kind of the property of having rational singularities in general, it's not clear how to do it, and the problem is that there is no obvious resolution of singularities in this section. Okay, so now I will explain the proof of this theorem. So how we derive, so from this algebra geometric statement, how do we derive this property of distributions, they're bounded. Okay, so for this we use this very beautiful picture of Bertrand integers, so which they did it for a fixed line bundle. So psi in their picture was trivial, but we also found it useful to vary psi. So we consider variety of pairs. So this is sometimes called yeah. So this is related to the subject of stable pairs or stable triples of bundles. When one considers a bundle together with a section. So, but here we also vary this line bundle psi. So there is a very stability condition for such pairs. So when you have rank 2 vector bundle with a section, so now if you have a line subbundle, there are two situations. This line subbundle may contain your section or not. So if your line subbundle contains a section, then you impose a stronger condition on degree. So then degree should be smaller than the slope of the line of the vector bundle given by this constant sigma, which is the real parameter. And if otherwise the conditional degree of the line bundle is weaker. So if the line bundle does not contain your section, then it's weaker. So now you can vary this parameter sigma, and you get a sequence of smooth varieties. And so when sigma is 0, this is just the usual semi-stability. So this corresponds to the rightmost variety PG minus 1. And on the other end, so if sigma is large, then the condition becomes simply that this section has no zero. So it's just an embedding of a subbundle. Right, so this means, so you have this sequence of varieties, so they're all birational to each other. The one on the very right has a projection to the modulus space of stable bundles. So this MS is stable bundles. You can just forget the section and just keep the vector bundle. And then I observe that this morphism from PG minus 1 to the modulus space of stable bundles with fixed determinant, this is exactly the morphism that has fibers, this variety is F sub B. So if we know our conjecture, well, actually, because we already know that all the fibers are of dimension are of dimension G, of the same dimension G. By miracle of flatness, we already know that this morphism is flat. But so our algebro-geometric conjecture is that members of this morphisms have rational singularities. And the idea is that then we will want to apply Eisenbach-Avni theorem to this morphism, and which will tell us that we can control what happens with push forwards along the fibers. So, but we start with the, yeah.
When the line bundle doesn't backwards in the section, why do you have this sigma there?
So sigma makes so the degree of A has to be even smaller. It's not smaller in the usual stability of bundles. It's smaller than the slope degree of
in the pair stability, if the line bundle backwards in the section, then it's the one that you go to the first one. But if it doesn't, normally it's just that.
Normally it's weaker. So sigma is a positive parameter.
Degree less than degree of B, but you don't need parameters. Is this nilpotent?
No. This was
Bradlow.
This is Bradlow Garcia Prado stability. Yeah.
What I'm saying is in the second row, I don't think for the second one they have that sigma. Not sigma. You don't need.
No. If there is no sigma in the second line, then every such V would have to be automatically stable in the usual sense. That would definitely be too much.
So for the.
No, you don't want. You want to include for some sigma. You want it to be allowed to be non-stable.
Okay. So for the large values.
For large values of sigma, you allow V which is non-stable, and that's exactly the point. So somehow when sigma is large, so if we don't vary this sign. When sigma is large, you just get a projective space. Okay, and you just have projective space of extensions. And on the other end, you just get the modular space of vector bundles with a section of stable bundles. Right. So now, okay, on the left hand of this picture, you start with projective. Not now in our picture, because we vary sides in the projective bundle over the Jacobian, where fibers are projective space of dimension 3g minus 3. So then the next step, P1, is going to be a certain blow up, and then starting from P1, going from P1 to P2, and so on, you're just doing some birational transformation for dimension 2. So you do not blow up anything, you just do some flips. And these flips have been completely described by Thaddeus as some explicit blow-ups followed by blow-downs. But also in Bertram's work, there is a description of kind of one big. So instead of going through the steps, you can just do one big blow up and then one big blow down. Either of these pictures works for us because we need some information on the corresponding exceptional loss rate. That's all provided by both pictures. Right. So now, so the point is that if we start with the left end, where we just have space of extensions, so there we have, so V is not necessarily stable, but so we get a map to this bundle, to the stack of bundles, just forgetting S. And this, because degree is 2g minus 1, one can check that this is a smooth morphism. So in particular, the push forward of Schwartz density will be Schwartz density. And somehow one can check that it's enough. So when we have to start with Schwartz density on stack of bundles and prove convergence of some integrals, so one can check that it's enough to consider Schwartz densities which come from the space P0. Okay, so that's the first step. So then we basically want to, so this is what we need to check. So we need to check that so inside this P0, which is space of extensions, we have the locus of stable bundles and open locus, and we have to consider the corresponding integrals of the corresponding orbits. We have to check that they're convergent and define bounded distribution. So basically, we want to go through this picture, through this Bertram-Thaddeus picture. We want to replace our Schwartz function P0 with some bounded distribution of PG minus 1. And then we would be just able to apply Eisenbach-Arnold theorem to this projection from PG minus 1 to MS and to the stable bundles. And if because we assumed algebro-geometric conjecture, we know that the fibers are going to be rational, we will have rational singularities, so therefore this will prove that push forwards are still bounded. Right, so the first step is to go from P0 to P1. There is some blow up going on. And so one needs to check kind of some relation between line bundles. First step. So because when you do this blow up, you actually change the family of bundles you consider along the exceptional divisor. And for this reason, the corresponding pullbacks of canonical bundles from the modulus stack of bundles, they differ by something on exceptional divisor. You have to calculate exactly the multiplicity of exceptional divisor that you get. And this is some standard calculation. And from this, you get that when you start with some density on P0, you do the blow up, so you get a density on P1, but you have to check what power of the equation of exceptional divisor you get. So O minus E, so it's generated by some local equation of exceptional divisor. So you need to check that this power that you get, this 4G minus 6 times kappa minus G plus 1, that it has positive real part. And indeed, this is the case. So when kappa is at least 1/2, this works. So then the next step is going through this ellipse. So you have to go from P1 to PG minus 1. And each time you go through a flip, you apply this lemma here, which tells you what happens. So if you start with some continuous function on X or continuous density on X, the claim, the conclude, you want to replace it by bounded distribution X prime. And so the conditions here, so the fact that you have a flip means that when you take a pullback of canonical bundle on X to this common resolution R, then it differs from the pullback of canonical bundle on X prime by some collection of divisors Di and positive multiplicities Mi here. So, and then on the other hand, we also have some multiplicities coming from line bundles, which are pullbacks of omega from the canonical, from the stack of bundles. And the claim is that if certain inequality for kappa is satisfied, then any continuous section on X will automatically give you bounded distribution of X prime. So here, indeed, this is the step where we cannot control so well the fact that we get a continuous function. So we can start with a continuous function, and then the function will be kind of more ugly. It will still be a bounded distribution, but so in the case of genus 2, this step actually is vacuous. So there P1 is already equal to PG minus 1, and that's the reason why in the case of genus 2, we're able to prove not only that we get a bounded distribution, but we actually get continuous functions. But in general, this presence of flips is kind of why we get a slightly weaker stage. Right, and so yeah, so we apply this lemma in our situation to this tedious flips, and we need to use precise description of the flips to check that these inequalities for kappa are satisfied, and then we apply this Eisenbach-Arnold theorem in a slightly kind of different version. So the usual theorem is that you take a Schwartz density on X, and then you push forward, you get a continuous function on Y. But if you just rewrite it in terms of distributions, you can see that it implies this fact about bounded distribution. The push forward with respect to such morphism preserves boundedness of the distribution of formal support. Okay, and yeah, finally, I want to say maybe a couple of words about checking this rational singularities property. So yeah, unfortunately, the case which we're interested in. So we have this very explicit scheme of P, but it doesn't seem to have any God-given resolution of singularities. So we know there exists one, but because we don't have any, there's not any particular canonical choice of which to look. We have to kind of resort to some tricks. And so we use two tricks. One trick is that the property of being having rational singularities is open under this kind of preserved under the formula. This was proved by Hecke. And another is the toric normal singularities are rational. So these two tricks turned out to be enough to know genus. So for example, if genus is 2, so we start with the rank 2 stable bundle of degree 3. So right, so then we have Jacobian, it's 2-dimensional, and then it turns out that our variety F is just going to be a blow-up of some 0-dimensional subscheme in Jacobian. This 0-dimensional subscheme in Jacobian is going to be local complete intersection, and furthermore, one can check that the tangent space, Zariski tangent space, is at most 1-dimensional, and this implies that it looks like this. So you have a smooth divisor, and then throw the divisor in the divisor, and then you blow it up. And such a thing is automatically, turns out that such a thing is automatically has rational singularities. Yeah, because it will be kind of described by this type of hypersurface singularities, x1, x2, all that with x3, and then you can degenerate this to a normal toric hypersurface that have rational singularities. Okay, and in genus 3, you have to work much harder. So there are a lot of cases to consider, but it's essentially, we essentially just, it's enough to use the same type of tricks. You kind of start with a singularity and you deform to, you specialize it to normal toric singularity. That's the way you look at this rational. But actually, I would be very happy if somebody will teach me some other tricks to prove that things have rational singularities. I mean, there are some kind of universal picture with determinant kind of schemes where you know that you have some resolution of singularities, but here we do some base change, and so things are kind of proved. So so at present, I don't know how to prove this in genus. It seems that for higher genus, our tricks are not sufficient. All right, thank you very much.